compressibility factor. Dear students, we saw that real gas deviates from ideal gas. Okay, real gas deviates from ideal gas, and the deviation of that real gas from ideal gas can be measured with the help of this compressibility factor. Deviation of real gas from ideal gas can be measured by compressibility factor. Okay, and this compressibility factor is denoted by Z. This is denoted by Z. So what Z is now? Z equals to PV real upon PV ideal. Because we told deviation of real gas from deviation of ideal gas is compressibility factor. So this is real gas and this is ideal gas. So for real gas and ideal gas we can write this. Hence the deviation, that is Z or compressibility factor, can be written as PV real by PV ideal. And you see what happens when we do PV real upon PV ideal. If this Z is equal to 1, okay, if Z becomes equal to 1, it is called ideal gas. And if this Z is not equal to 1, then it is called real gas. If it is not equal to 1, it is real gas. Now what we can write, since according to ideal gas PV is equal to nRT. PV is equal to nRT. For this is PV for ideal gas, this is PV ideal. So we can write in case instead of PV ideal as nRT. So Z is equal to PV real, or simply we can write it as PV now because we are writing in denominator as nRT. So this will be PV of 1 nRT. Okay. So this is the equation for compressibility factor, and it indicates that if in a question the pressure, volume and temperature of a gas is given, then we can find Z, and if Z is equal to 1, it will be an ideal gas, and if Z is not equal to 1, it will be a real gas. Now suppose, so this is for n moles of gas. If we take this for 1 mole of gas, we have to divide n in both these. So this will be PV by n, and this will be nRT by n. So what happens? Suppose this is called PVM and it will be RT, where what? V by n is equal to Vm, and it is called molar volume. Okay, so our Z now becomes PVM by RT, and this is for 1 mole of gas. Okay, so this is for 1 mole of gas. Let's write all these equations, needed equations here, like Z equal to PV by nRT, again Z equal to PVM by RT, PVM by RT, but this is for 1 mole, and to add something, this is also very needed. Z equals to PV real by PV ideal. Okay. Now you see we wrote Z equals to PV real upon PV ideal. So we can write inside Z equals to PV real. Suppose we are writing this like this, and PV ideal. Okay, and if we consider this for 1 mole of gas, it will be simply like PVM for real gas and PVM for ideal gas. Okay, and it is Z. So now at constant pressure, what will happen? At constant pressure, this pitops will be now cut. Okay, so the Z is equal to Vm or molar volume of real gas of 1 molar volume of ideal gas. So this is the term. And dear students, you all know that at standard temperature pressure condition, that is called as STP, the Vm or volume of ideal gas is 22.4 liter. So what we can write here is Z equals to V real, this is Vm real, let's write Vm real of 22.4 liter. Okay, but remember this is a STP. Okay, this is STP condition. Now you can see here, if at STP Vm equals to 22.4 liter, then what will be Z? If you quote Vm equals 22.4 liter, that means if at STP the volume of a real gas is equal to 22.4 liter, then that gas is not real gas, rather it will be ideal gas, because Z will be 22.4 divided by 22.4, that equals to 1. And we had and I had told that if Z equals to 1, that is ideal gas. So here it will be ideal gas. Okay, and if Vm is less than 22.4 liter, okay, if Vm is less than 22.4 liter, then what will happen? Z is less than Vm real divided by 22.4. Okay, so Z will be less than Vm real by 22.4. So Z is less than, stop here, this is Vm real by 22.4 and Z is less than, so here what we will found is that this is less than 22.4 liter. Okay, this is less than 22.4 liter. So this is going to be, suppose like this is 20. Okay, so 20 by 22.4. So you can write actually here Z equals to Vm real by 22.4 liter, and we are saying that this is the second condition, that Vm is less than 22.4 liter. Suppose as an example Vm real is 20 liter, so we will get 20 by 22.4, that is less than 1. So Z will be less than 1. Okay, when Vm is less than 22.4 liter, Z is less than 1. And what happens when Vm is greater than 22.4 liter? We will get Z equals to something like, again, Vm real divided by 22.4, whereas this term is greater than 22.4 liter, so we are getting Z is greater than 1. So you see, here we got three things: Z equals to 1, Z is greater than 1, and here Z is less than 1. Then what does this indicate? What is mean by Z is less than 1? What do you mean by Z is greater than 1? And what do you mean by Z is less than 1? Let's understand this properly. But write this equation first over here. Z equals to Vm real divided by Vm ideal. Okay. So now let's understand significance of Z equals to 1, Z less than 1, and Z greater than 1. Z greater than 1. Okay. When Z equals to 1, the gas is an ideal gas. Okay, the gas is ideal gas, and for this the net volume of gas molecules is 0, and the intermolecular force of attraction, or you can write attraction force, is equal to 0. Okay, but when Z is not equal to 1, here Z equals to 1 is ideal gas. Okay, when Z is not equal to 1, this is real gas, and when Z is not equal to 1, it has two cases. First case is Z less than 1, and second case is Z greater than 1. Okay, now let's understand these two cases. Z less than 1, what we write is Z equals to Vm real upon Vm ideal. Z equals to Vm real upon Vm ideal, and if it will be less than 1, okay, so what we found is less than Vm. What we found is that Vm real is less than Vm ideal. It means that the volume of real gas is less than the volume of ideal gas. Means it's easy to compress the real gas now. It means that easy to compress gas, and if it's easy to compress gas, we can also say it's easy to liquefy the gas. Easy to liquefy. And what if it is easily liquefied? It means there is an attractive force between the gas molecule. So we are able to liquefy it easily. Means there is an attraction force between the gas molecules. So what? Attractive force present. Okay. Now let's calculate this. Let's rub this. Now let's calculate this. What will happen in case of Z greater than equals to Z greater than 1? Again, Z equals to Vm real divided by Vm ideal, and this is greater than 1. So Vm real is greater than Vm ideal. Okay, so it means that the volume of real gas is more than the volume of ideal gas. So how it will be possible? The volume of real gas, if the volume of real gas is more than the volume of ideal gas, that means that it's difficult to compress the gas now, because we have a higher volume of gas. Okay, difficult to compress. And if it is difficult to compress, that means it is difficult to liquefy. Difficult to liquefy. And if it is difficult to liquefy, that means a repulsive force exists between the gas molecules. Repulsive force present. Okay, so dear students, we discussed all about what is Z less than 1, that is in case of ideal gas, where attraction force is 0. When Z is not equal to 1, it has two cases, Z less than 1 and Z is greater than 1. If Z is less than 1, that means the gas is easily compressed and it can be easily liquefied, that means an attractive force is present. And if Z is greater than 1, then it is difficult to compress, that means the gas is difficult to liquefy, and it also indicates a repulsive gas is present. Repulsive force is present. Now, dear students, let's draw some graphs for. Now let's draw some graphs for Z, that is compressibility factor. Okay, versus pressure. Z versus P graph. Okay. Let Let's take pressure in x-axis and compressibility factor, that is Z, in y-axis. So let here Z equals to 1, that is ideal gas condition. Z equals to 1 here. We will find this graph for helium and hydrogen gas. Okay. This will be the graph for CO2 and this will be graph for N2. Actually these things are experimentally found. I am drawing some of the Z versus P curves for different gases, and remember here temperature is constant. Okay, at constant temperature for different gases we are drawing Z versus P curve. Okay student, so can you tell me one thing from this curve now, that which gas is easily liquefied? You see here the Z value is lowest for whom? This is the lowest Z value, and this is for CO2. Okay, for CO2 Z is less. For CO2 Z is minimum. And now just before we read that when Z is less than 1, the gas is easily liquefied when Z is less than 1. That means among these gases CO2 is easily liquefied. Okay, so CO2 Z is minimum, so CO2 is easily liquefied here. Okay, now let's see another thing what we are observing from graph. Another thing that we are observing is that Z is greater than 1 for helium and hydrogen over entire range of pressure. What is our first observation? Our first observation is Z greater than 1 for helium and hydrogen over all pressure. Okay, and our second observation is, see guys, for these other gases at low pressure, okay, at low pressure condition, suppose this at low pressure condition, here it is low pressure and it is high pressure. Okay, so see here at low pressure Z is less than 1. This is less than 1, this is less than 1, this is less than 1, I mean this point. Okay, so Z is less than 1 for other gases. Z is less than 1 at what? At low pressure. At low pressure for other gas. Okay, and you can see here Z is greater than 1 for other gases at high pressure. Okay, Z is greater than 1 at high pressure for other gas. So now our job is to verify all these things through van der Waals gas equation. How Z is greater than 1 for helium and hydrogen over entire range of pressure, how Z is less than 1 at low pressure, and how Z is greater than 1 at high pressure. So let's write the van der Waals equation first. According to van der Waals equation, P plus an square by v square into v minus nv equals to nRT. You must remember this is the van der Waals equation that I have derived some time before. Okay, so if we consider this for 1 mole of gas, again we will get molar volume, and that will be P plus A by V square into Vm, that is molar volume, minus B, that equals to RT. Here the volume is also molar volume. Okay. Actually, let's write this here. Z greater than 1 for helium and hydrogen. Z greater than less than 1. Z less than 1 at low pressure, and Z greater than 1 at high pressure. Okay. So now see, first let me do this from here. At high pressure, what will happen? High pressure. What will happen at high pressure? At high pressure, this A by Vm square term can be neglected, because since the pressure is high and this is a small term, we can obviously neglect this A by Vm square. So it will be at high pressure P into Vm minus B is equals to RT. Okay, because we neglected A by Vm square. So this will be PVm minus PV equals to RT. If we divide RT in both the sides, PVm by RT minus PV is equals to 1. Or here, let's remember, dear students, PVm by RT was Z. So Z equals to 1 plus, this is PV by RT, 1 plus PV by RT. Okay, so Z equals to 1 plus PV by RT. Okay, for P is pressure, B is constant, R is gas constant, T is temperature. So obviously it is a positive term. Since this is a positive term, 1 plus positive term is greater than 1. So here Z is greater than 1. And we found at high pressure Z is greater than 1. Okay, it's verified. Now at low pressure, what will happen at low pressure? In high pressure, we neglected A by Vm square because P was high. But here pressure is low, means we cannot neglect A by Vm square as respect to P. So P plus A by Vm square into, but see here, since pressure is low, volume is now high. Okay, and since volume is high, what we can do is that we can neglect this B term in terms of Vm. So if we neglect B, it will be Vm, and this is equals to RT. Implies that PVm plus A by Vm, that equals to RT. If we again divide RT, PVm by RT plus A by Vm RT is equal to 1. Again, PVm by RT is equal to Z. So Z is equal to 1 minus A by Vm RT. And since this A by Vm RT is a positive term, if we subtract it from 1, we are getting less than 1. So this is now less than 1. So what we found is that Z is less than 1. So at low pressure, Z is less than 1. Okay. Now what happens for helium and hydrogen? Dear students, what happens is that in case of helium and hydrogen, we get an dipole-dipole interaction. But this dipole-dipole in case of helium and hydrogen, we don't get any dipole-dipole interaction because this is a non-polar molecule. Okay, so here no dipole-dipole interaction. And again, the van der Waals force in case of helium and hydrogen is also 0, because van der Waals force exists between molecules if it has a higher surface area. And since helium and hydrogen are small molecules or small atom, in this case its surface area is very low. So we get a van der Waals we get a van der Waals force 0. 0 van der Waals force. So what happens in case of helium and hydrogen? We get 0 van der Waals force, also no dipole-dipole interaction. It means that the intermolecular force of attraction, that is A, is equal to 0. So for helium and hydrogen, A equals to 0. Okay, and since A equals to 0 here, this is equals to 0. So again, we told that A equals to 0. So if A equals to 0 here, this term will be 0. So again we can write this, and in case of V minus NB, again Vm minus NB is there, and if we again solve it, we get Z greater than 1. So for helium and hydrogen, Z is greater than 1. So students, this was all about compressibility factor.